Hi, I'm Daniel Chan from UNSW Sydney. Welcome to another adventure in pure mathematics. In this video, I want to show you how, if you're given a Lie group action on a manifold, we can get differential operators out of that. And in so doing, what this will allow us to achieve is we can describe the universal enveloping algebra of GLN as differential operators, not on the Lie group, but rather just on Cn, okay, which is a much easier thing to do and look at. Okay, so what's the key idea? Let's set our notation. G will be my Lie group, and we're going to assume that it acts on a manifold M, and we'll assume actually the action is on the right. That's probably the easier way to do things. Okay, so let's start now with an element V, which is in my Lie algebra G. Remember, that's just the tangent space to the Lie group at the identity. And what this will do is this will actually give me a one-parameter group of transformations on M. Okay, so how does that work? So we're going to use the action of G on M. Okay, so one parameter group of transformations just basically means an action of R on M. And what is that action? Well, we're going to restrict basically the action of G to a one parameter subgroup, and that one parameter subgroup is the one corresponding to V. In other words, if we have T as a real and M is a point, that gets sent to what point here? Well, we take that M and we let X of TV act on it. X of TV. Okay, so that's what we have. And this is clearly a group action. Essentially, we've just restricted this group to action of this one parameter subgroup. And since we have this one parameter group of transformations, we can essentially get a vector field Vm on M. Okay, so how do you get that? Essentially, what you do is you just differentiate this with respect to t, and the value at t equals 0 will give you a tangent vector at M there. Okay, so that's your tangent, that's your vector field. Okay, so the value at any particular M, you just take the derivative of this, and that will give you what that vector is at that point. Okay, so let's look at two simple examples of this sort of setup. The first one is the right regular action. Okay, so that just means that G acts on itself on the right hand side though, so R equals G. That means TG gets mapped to G times the exponential of TV. Okay, and if you think about this, okay, we can go through this procedure. There's your one parameter group of transformations, okay, the group G acting on itself. And here what happens is you see that you also get a vector field now on G. And what vector field is that? It's actually just the left invariant vector field associated to this Lie algebra element V. And it's probably what you would have expected, right? Because that's the natural vector field that you can cook up from there. And to check that this is true, just remember, okay, so this is, if you look at the left invariant vector field associated to V, okay, how can you get it? So firstly, remember this XTV, that's going to be the integral curve of this vector field. Okay, that's an integral curve. And essentially what happens is that since it's left invariant, this vector field should be such that it takes integral curves to integral curves. So here, if I want to find out what's the integral curve that goes through G, I just hit it on the left, okay, by G, and that gives me the new integral curve. And that's why we see from this that this is indeed, this VG is the vector field, which is the left invariant vector field associated to this Lie algebra element V. Okay, so let's do a slightly less abstract example, and one that hopefully will make all the objects here quite concrete. Okay, so here we're going to look at G is just the general linear group of real 2x2 matrices, GL2R, and it acts on M, which is going to be R2, just by matrix multiplication. We want it to act on the right, so we'll think of these as row vectors. Okay, that's how we'll do that. And I'm just going to pick a particular element inside the Lie algebra. So remember what the Lie algebra of this GL2R is. The Lie algebra is just the set of all matrices inside here, all 2x2 real matrices. Okay, so in particular you have 0, 1, 0, 0. Okay, that's an example of something in this Lie algebra. Okay, so we've got the setup of what we have here. So that means that we can generate firstly a vector field on R2. And from that vector field, we can get a differential operator. So let's see what is the differential operator associated to this. Okay, you'll see that it's something that's actually quite a familiar type of object here. Okay, so here we'll call this differential operator d subscript Vm. And we're basically differentiating functions on R2. So functions of x1 and x2, say. So what is the derivative of this f? The derivative with respect to this vector field here. Okay. So what do we do? So firstly, we take this function and we're going to apply to the variables this xtv. Okay. So basically, we look at this right regular action and we apply it to the point inside here. So what's x dot tv? So we've got to multiply this by t, so that gives you 0, t, 0, 0, and we exponentiate. And that exponential is quite easy to work out. It's going to be, no, that's not a 0 there, it has to be an invertible matrix. Okay, so it's not a 0 there. It's going to be 1, t, 1, 0, like that. Okay, so that's something that's quite easy. You just use the power series if you like. So you have 1 down the diagonal. You have add to that the vector. And then if you look at the square of this, of course, and all the higher powers of this, you'll get 0. So there are no extra terms in that power series expansion. So that's what you have here. Okay, so let's multiply this row vector with this 2 by 2 matrix and see what the new value you want to evaluate this f at. Okay. So remember, you have this function, and now we've multiplied it by this element in this one parameter group. Okay, and remember, to get the value of the derivative, you need to differentiate with respect to t and evaluate that derivative at t equals 0. That's what you want to do. Okay, so let's multiply these two first. So what do we have here? So I guess you have 1, 0 times this one. So you've got x1 in the first slot. And then you have t1 in the second variable here times this. So we have t times x1 plus 1 times x2, t times x1 plus x2. So we want to differentiate this as a function of t at t equals 0. And that's quite easy to do, right? Okay, so the t only occurs here, so we just have to differentiate this with respect to the second variable here. And then since this second variable is t x1 plus x2, right? We need to differentiate this second variable as a function of t as well. So this is linear in t, it's x1 times t plus x2, so you get an x1 popping out. So the value of this here is going to be just x1 times df dx2, and that's evaluated at x1, x2. Okay. So what have you done to this function of two variables x1 and x2? What does this differential operator do? All it does is it differentiates partially with respect to x2 and multiplies by x1. It's this differential operator, which you can write very easily as x1 d dx2. Okay? It's something that's very, very understandable. Okay? And that's the differential operator you get on this R2 here. Okay? So here we see that, yeah, we just put it in a element of the Lie algebra, and then it's going to give us a differential operator on this manifold. Okay. So let's set up some notation so that we can talk about the general picture of what we will get. Okay. So if we have a vector field on M, let's call it W. Okay. We're going to let dW be the differential operator that's associated to that vector field. Okay. And then this script D of M will be the ring of differential operators. So here I'll just mean by that the ring that's generated by all these differential operators dW, where W varies over all the smooth vector fields on M. Okay. And the wonderful fact that we have here is the following. Okay. So there's actually a ring homomorphism from the universal enveloping algebra of this Lie algebra G to the differential operators on M. And how do you define it? Okay, so there's a ring homomorphism. Well, remember, what are the generators for this universal enveloping algebra? Well, you just have to pick a basis for this G. In particular, this Lie algebra G is a set of generators for this universal enveloping algebra. So if I tell you what it does on all the elements of G, the Gothic G here, the Lie algebra, then it will define this for you. Okay, there's only one possibility for what it is. And what is that? It's basically you send that vector v to the corresponding differential operator which is associated to the vector field Vm. So remember what we did here was we created for each element of the Lie algebra, we created this vector field Vm on M, and that gives us a differential operator. Okay, so here we saw what happens if the Lie algebra is the space of 2 by 2 real matrices, so this element will get sent to this differential operator. If you pick other elements, I hope you can kind of guess what type of things you should get. You get other differential operators, okay? And that extends to a ring homomorphism, okay? So to check that it extends to a ring homomorphism, there's various ways to do it. I'll show you a heuristic argument later why you expect this to be true. But I guess one way you can prove that this is actually a ring homomorphism is to check that the relations here, and we know what the relations are, they're given by the lead bracket. Okay, the relations here get sent to 0 here. And that gives us this wonderful fact that we have here, which allows us in particular, for example, to study this universal enveloping algebra. Okay, because you have a homomorphism from here to here, and maybe the differential operators here are easier to study. Remember, if you look at this GL2, okay, this Lie algebra here, and it's universal enveloping algebra. Okay, normally you think of them as left invariant differential operators on this Lie group. But now here I can map this over to differential operators on R2 to a differential operator like that, and that's a lot easier to understand. Okay, so let's have a look at an example of this ring homomorphism phi that I mentioned. And we'll also see how this allows us to help us understand the universal enveloping algebra. What I want to do is I want to go back to that second example that I mentioned before, but extend it a little bit. So here, instead of just GL2, we look at GLNR, okay? And then, of course, this will now act on Rn, where we think of this as row vectors, and we multiply by these n by n matrices on the right. And the fact that I gave you gives a ring homomorphism from the universal enveloping algebra of this Lie algebra GLN to differential operators on Rn. And so we saw in the special case what happens when n equals 2. Okay, we saw one of the standard basis matrix, so 0, 1, 0, 0, got sent to x1 d dx2, and I hope you can kind of sort of guess how generally this map should work. So what happens is that if you let Eij be the standard basis matrix, which has a 1 in the ith row jth column position and 0s elsewhere, okay, so this is an element inside this GLN, okay, and it's a basis vector, it will get sent to xi d dxj, which is clearly a differential operator on Rn here, okay. And actually you can show that this ring homomorphism is injective. So another way to think about this universal enveloping algebra is you just look at the algebra that's generated by all these differential operators on Rn. Okay, so that's rather nice that this universal enveloping algebra has this simpler description over here. And I want to use this simpler description to give some modules over this, okay? So, so how are we going to do that? So what I'm going to do is I'm going to introduce this space of polynomials. So my x tilde here will be just shorthand notation for the variables x1 up to xn. So I can look at the polynomial ring in these n variables, and I'll just look at the degree d part of that. So that's the space of degree d homogeneous polynomials. Okay, so just to be precise about what that means, suppose you have a monomial of this form, x1 to the i1, x to the i2, xn to the in. Okay, we say that's degree d if the sum of these i's, indices, is equal to d. Okay, and we just look at the span of all these monomials. Okay, so and that'll be the complex span, okay, of all these monomials. So that's going to be a subspace of this vector space of polynomials. And I claim that, in fact, it's a module over the universal enveloping algebra of UGLN. Okay? And to do that, I guess all I need to do is to give an action of this UGLN on this space here. And the way I'll do it is I'll give an action of the corresponding differential operators on this side. So Eij is just going to act by xi d dxj, okay? And I claim that that's an action, okay? Well, certainly these differential operators will act on the space of all these all smooth functions, and the key point is that these operators preserve this subspace, Okay, so why does this preserve this subspace? So what does this differential operator do? Okay, firstly you have a d dxj, and that will reduce the degree of this polynomial by 1. So it goes down from d to d minus 1. But then you multiply this by xi, which lifts it back by 1, so it goes back to d. Okay, unless you get a 0, which is possible, but that's in that space. Okay, so that means that you'll get something that's degree d again. So that means that these differential operators actually preserve this space, and so too will any sum and product difference also preserve this space. So in fact, this is actually closed under action of all these differential operators, and hence under the action of this universal enveloping algebra. And so we've actually constructed a module over this universal enveloping algebra. And the nice corollary about this is that we have this Lie algebra Lie group dictionary. So in particular, that tells us that this space of degree d homogeneous polynomials is actually a module over GLN. Now, if you know a little bit more about tensor products and representation theory, actually this is not such a surprising result, but it's nice to see it exhibited in this way. Okay, so of course a natural GLN module that you have is Cn. Okay, it just acts by multiplication, and you can take tensor products of representations to get representations, and then you can also take symmetric powers. So if you take the d symmetric power of this, okay, you will get precisely this representation here. Okay, so now what I want to do is I want to try to explain where the fact comes from. Why do you expect such a ring homomorphism? And the key case, I guess, is to look when G acts transitively on your manifold. So when it acts transitively on your manifold, that means it's just a G orbit, and you can classify a G orbit. So I just want to think, just specialize to the case where M is going to be the quotient of G by the stabilizer of some point, so basically some closed subgroup H, okay? And I'll write the subgroup on the left here because I want the action to be on the right, okay? So here we have some G, we have the Lie group, we have some closed subgroup H, and we want to look at these right cosets, okay? So this is a set of right cosets, and we have an obvious quotient map which sends a group element to this right coset containing it. Okay, so there's our pi. We want to differentiate functions on this manifold, right? We want differential operators on this manifold. So to think about those functions, let's consider the pullback map, pi upper star, okay? So you have a map like this, so we have a reverse map on functions. So if you have a smooth function on G mod H, that maps to a smooth function on G by this pi upper star. So a function here gets sent to what? So here you have a function which has inputs in here. What you can do is first you map G to G mod H, and then you apply that function. So you apply that F. And that's my pi upper star of F. Okay, so hopefully you've seen this before, but if not, actually it's a very simple idea, and I'd like to explain it like this. Okay, so suppose you have a function on G mod H. That means that you input orbits like this, okay, or rather cosets like this. The elements of here are coset. For each coset, you give a value. Okay, so for each coset, you give a value. And what you can do is, rather than inputting these cosets, you can input points of G, like any point here, and you'll get a new function where the value at that point is going to be, well, you just let it be the value on the coset that contains it. Okay, so essentially that's what all this function does. Okay, you're saying, oh, okay, so you have a function on this G mod H. Essentially you have values on each of these cosets. So you can think of a function on the whole of this group, okay, and what happens is they're going to be constant on these cosets. So in other words, functions on G mod H, they're essentially just functions on G which are constant on the right cosets of H. Okay, and the second bit is, well, I'm going to give you a new interpretation of what this map phi does, okay, in this special case. So it's a map from the universal enveloping algebra of G, Gothic G, to differential operators on this manifold, which in this case is homogeneous, so it's a G mod H. And I claim it's essentially just, so here you're thinking of differential operators on G, so you're differentiating functions on G. And here you're differentiating functions on G mod H, okay? But I said these functions are just a subspace of these functions here, and I claim that this map is just restricting the differential operators here to differential operators on this subspace. Okay, that's all there is to it. Okay, so let's see why that's true. Okay, so let's just see what's happening if I want to look at the differential operators on here. Okay, so we pick a function on this g mod h. Okay, there's a function on this g mod h, and we want to differentiate it. So we pick some vector v inside our Lie algebra. Okay, that gives me a vector field on this manifold M, and hence a differential operator. Let's differentiate this f with respect to this dvm and see what we get. So remember how this derivative works. Okay, differentiation works. Okay, so firstly, you look at this input value and you hit it with xtv. That's where the vector comes from. Okay, you hit it with xtv and you evaluate f at all these points for all these different values of t, and then you take the derivative of this function of t now at t equals 0. Okay, so this is the function value on this coset. So of course you can think of it, right, as a function on g using this pi upper star. Okay, so this is the value, this function value here is just pi upper star of f of g exponential times g exponential of tv. So remember what pi upper star of f is. Firstly, you apply pi. If you apply pi, you just take this to its coset. Apply pi, you just take it to the coset containing it here. So that's this one here, and then you apply f. So these two are the same. Okay, what's inside this and what's here. And then you just differentiate this. But what is this derivative here? So what you did was you just applied, we might multiply this g by this xtv. Okay. So basically this is the integral curve corresponding to this left invariant vector field v. Okay. And we're going to differentiate along that. So that means that you're just differentiating with respect to this vg, this pi upper star of f. So this vg, of course, is just the differential operator back up on here. And we're just applying this differential operator on this pullback function. So essentially, the image down here is just a restriction of the differential operator upstairs. And there you have the explanation for why you expect this to be a ring homomorphism, because essentially you're just restricting the differential operator to some subspace of functions. And this is the homomorphism which allows you to study the universal enveloping algebra in particular. And as you can see here, for example, it gives us fairly cheaply these modules. I hope you enjoyed this adventure in pure mathematics.